She then started at a postdoc at the Department of Applied Math in the Research School of Physics at the Australian National University, where she has continued to look at post-scale physics with applications in CO2 storage and CO2 utilization. And there she has continued to develop an approach for post-scale characterization based on topological analysis of 3D images data. She was awarded a Discovery Early Career Research Award Fellowship from the Australia Research Council in 2018, and she's also a chief investigator for the Australia Research Council Training Center for Multiscale 3D Imaging, Modeling, and Manufacturing at the NU. Her talk today will focus on a topological data analysis method, persistent homology, and how this can be used to characterize fluid microstructure. Okay, Anna, now the floor is yours. But before that, I'm wondering, you prefer people ask a question in between or at the end?
Oh, if people are happy to speak up in the middle of the talk, that would be great.
Okay.
So yes, questions anytime anybody has a question is great.
Okay, thank you. Then Anna, the floor is yours.
Thank you. Yeah, thank you very much for the introduction, and thank you also for inviting me to come talk to you all. This is a really nice opportunity. And also thanks to everybody for showing up early. I think this isn't your normal seminar time, but you know, because of the time difference, it's already evening here in Australia. So I really appreciate everybody showing up early to listen to the talk. And yeah, today I want to talk about topological data analysis and persistent homology and how we can use this to reduce uncertainty and error in topological measurements. Okay, so I want to give a quick introduction and some basic definitions so we're all on the same page. Topology is a branch of mathematics which quantifies the connectivity of objects. So there's no geometry information, no shape information, it's just connectivity. Values that are commonly measured include the Euler characteristic. Can you see my pointer on the slide? Okay, so the Euler characteristic is indicated by chi and the Betti numbers. So there are 3 Betti numbers that we're interested in 3 dimensions. So Betti 0 is the number of discrete objects. Betti 1 is the number of loops or redundant connections. And Betti 2 is the number of cavities or inclusions within the object that you're looking at. The Euler characteristic or the Euler number is just the alternating sum of these Betti values. So the classic joke here is that to a topologist, there's no difference between a coffee cup and a torus because they both consist of one object with one loop. So a Euler characteristic of 0. Okay, so when we're thinking about fluid structures, oh, it says it can't play. Okay, sorry, there is a video here, but I guess for some reason it's not playing. But the goal with the video is to show you sort of fluid structures and these different topological features that you might see, like a fluid phase inside of a porous media manifesting as some of these topological features. So when we're thinking about fluid microstructure, we can apply the same quantification. And for most studies, we focus on the non-wetting fluid phase, and that's also what I'm going to be looking at today. So basically, we want to count up the number of individual non-wetting phase ganglia or bubbles, and then also the number of redundant loops or the number of redundant pathways that the fluid is connected through. And in the case where we only have 1 or 2 fluid phases, which is what I'm going to consider here, for a non-wetting phase that's inside of a porous material, it's physically unrealistic that we would see these Betti 2 features. So a common assumption that's often made is that we can neglect Betti 2 features when we're looking at non-wetting phase. So instead, we're really just focusing on the trade-off between disconnected components and numbers of loops. Okay, so here's an example of topologically simple fluid ganglia. So in all of these cases, the Euler characteristic is 1. So there's one object in all these cases, but no loops, no cavities. And that means that all of the topological laws that apply, for example, to this near spherical droplet also apply to these other ganglia, which may have more complicated morphologies, which might be dictated by the media that the droplet is confined within. Here are some examples of some more topologically complex fluid structures. So this is a non-wetting phase visualized during an imbibition experiment. So the non-wetting phase saturation is decreasing from left to right as we're undergoing imbibition. And you can see that in the two cases, well, the case on the left and the case in the middle, we have this well-connected fluid phase, and that's indicated by these Euler characteristic values, which are large negative numbers. So a negative Euler characteristic just indicates that there's more redundant loops, more redundant connections than there are individual components, indicating that the fluid structure overall is well-connected, well-interconnected. And that's in contrast to the case over on the right, where we have a lot more disconnected components than we do loops, and we then have a positive Euler characteristic, indicating that the fluid phase here is dominantly disconnected. And the Euler characteristic and the Betti numbers are additive. So you can measure these values for each individual cluster or each individual ganglion inside the system. And you can look at the topology on a per ganglia basis. But we can also measure these values for the global system. And the value for the global system will be the sum of all the local individual components. Okay, so that's my rapid introduction into topology and how it relates to non-wetting fluid phases. And that brings us to the motivation for this current study, which is that there has been an increasing prevalence of the use of topology in the characterization of porous materials and fluid structures. And this started about 25 years ago, but it's been increasing more rapidly recently. So here I have some papers ranging from the early 2000s to more recent ones, where researchers have used topology and metrics like the Euler characteristic, Minkowski functionals, to describe porous structures and pore space configurations. Then in 2013, I was part of one of the first groups that used topology to describe fluid structure. So not just the porous medium, but also the fluid distribution inside the porous medium. And in those cases, we were looking at how that would relate to capillary trapping. Since then, there's really been an explosion in studies that have used the Euler characteristic or Betti numbers and also the Minkowski functionals to describe fluid configurations related to different flow patterns, different flow regimes. It's been incorporated into thermodynamic models related to absolute permeability and effective permeability, and also used to help characterize other media properties like wettability. So this isn't an exhaustive list at all, but these are some examples that I had handy. So the point, I guess, is that people have really started to recognize the usefulness of this kind of characterization. And a lot of these studies are based on image data and maybe more specifically on computed tomography data, on X-ray CT data. So now it becomes very important to understand how inherent imaging artifacts and image processing can impact quantitative results. So that's what I'm interested in this current study. So I'm going to give you some examples of some of our experimental imaging results. And so I want to give a few details about the experiments. So in this set of experiments, we looked at a Bentheimer sandstone imaged with X-ray microCT at the ANU CT lab. The imaging setup that we used was novel for the ANU CT lab in that we used a region of interest imaging in combination with a helical space filling acquisition trajectory. So this allows us to get a pretty good resolution. So we're close to 1.7 micron voxel size, but we're still able to image a tall, large volume. And in this case, the total volume that we imaged was almost 200 cubic millimeters. Because of the acquisition trajectory, we're able to minimize imaging artifacts. So that gives us these really nice sharp images. We're actually starting to visualize the porosity inside the clay phases. And we're avoiding phase contrast artifacts at the interfaces between different materials and also avoiding vertical variation and attenuation. So we don't see distortion or otherwise, bad data at the vertical ends of the data set. And in this case, we're looking at 4 different data sets. So we have a scan of the dry rock and then 4 partially saturated states through this imbibition process. So this is a radiograph of the flow cell as it's sitting inside the microCT. So you can see the rock that's in the center of the cell, and then you can sort of see these shadows of the flow cell on the edges. I'm going to try to show, okay, so this video works. So this is a series of difference images of the 2D radiographs as we're like letting droplets of water come in contact with the rock and get pulled into the rock. So because it's a difference image, where the bright color appears, that's where new water has appeared in the image and is getting pulled into the rock. I'll just play that one more time. So you can see that there's like the brine meniscus that's at the very bottom, and then once it makes contact with the rock, the water sort of gets sucked up into the rock immediately. And then there's a slower re-equilibration period. So this has been sped up. So that video was originally about 5 minutes long. Here's another fluid injection that was later on in the experiment. So you can see that at this point, we have water films that are established all the way throughout the pore. So as soon as that water meniscus makes contact with the rock, the water distributes throughout the rock almost immediately. So it's growing those existing water films and filling in the pore spaces. Okay, so going back to the data, this is, of course, a 2D slice, but it's from our original 3D microCT data set. And then we can process this to get 3-phase segmented images. So here's our segmentation. Black is air bubbles, the teal color is brine phase, and then the olive is solid grains. And then I'll just flip them back and forth so you can kind of see the segmentation results. And so this is the data that all of this analysis is based on. Okay, so with this experimental data, we can start to look at how topological quantities are impacted by imaging details. So we calculated these classic topological values for the non-wetting phase in the segmented data sets. And here I'm showing some of the results for the dry scan and also for the lowest wetting phase saturation scan. So this is basically 100% non-wetting phase in the dry scan, and then 89% non-wetting phase in the second scan. And so what we noticed when we were first calculating the topological values is that we're getting really large numbers of Betti zero features. And we thought that this is because we're actually starting to pick up this microporosity in the clay phases. And so we end up getting huge numbers of disconnected components, which is really associated with potentially unresolved porosity that's in the clay phases. So we applied a fairly conservative, size filter, threshold size filter. So we removed any isolated objects that were smaller than the equivalent of a sphere that was 9 micron radius. And so basically when we do that, when we throw away those very, very small non-wetting phase features, we see a very large difference in our calculated topological values. So for the dry scan, we go from 77,000 Betti zero features down to 1,400 Betti zero features. The Betti 1 features, so that's the loops that are present in the system, that number doesn't change very much. But because the Euler characteristic, of course, depends linearly on both Betti 0 and Betti 1, we also see large changes in our Euler characteristic values. So, and in terms of the volume normalized Euler characteristic, there's a difference of an order of magnitude when you do this, pretty small level of noise removal, or if you don't. And in terms of this second scan, the one that has the microporosity or the small features removed, the absolute value, the absolute change in terms of Betti 0 and in terms of Euler characteristic isn't as large, but it's still really significant because we go from having a positive Euler characteristic when we leave those small features in to a negative Euler characteristic once we remove those small features. So this really changes our interpretation of whether the air in the system is connected or not, depending on whether we're including those very, very small features or not. Okay, so another length scale relevant issue that we might need to consider when we're working with image data is our image resolution. So with the data that we acquired in this set of experiments, we did a digital downsampling on the grayscale data, and then we resegmented the resulting grayscales to see how that would affect these topological measurements. And I'm just zooming in on this zoomed in region just to highlight that as we're going through this downsampling process, we're losing very small features. So we're going to start losing like the very thin pore throats and the crevices in the rock. And as we get to larger voxel sizes, we're also starting to see different features merging together. So these grains aren't separate anymore, in either of these ones. And that's also what we see in the quantitative data. So here I'm showing Betti 0, Betti 1, and the Euler characteristic with the voxel size on the x-axis. So the high resolution data is on the left, and then the artificially coarsened data is moving to the right. Black is for the dry scan, and then the different colors are the different saturation states. So as we coarsen the resolution, we're averaging out small features. We're losing the thinnest pore throats, so we are disconnecting what was originally connected pore space. So that leads to this increase in Betti 0 features. We're also losing Betti 1 features, so we're losing those small pore throats. And then when we get to really large voxel sizes, when we get those merging of grains, we start to see like the creation of new artificial loops. Although that's not as significant maybe. But the end result is that the Euler characteristic changes pretty dramatically when you coarsen the resolution, although this does depend on saturation level. Okay, so these are all issues that are associated with feature size. So it would be useful to link topology with length scale. So that brings us to the titular topic of the talk, which is persistent homology. So homology in this case means similar structure, more specifically similar topological structure. And the phrase persistent indicates that we're measuring how these structures persist over a range of length scales. So persistent homology seeks to answer the question, over what range of length scales does an individual feature maintain its same topology? Okay, so I'm going to try to explain how the persistent homology technique works. First, we start with a two-phase segmented data set. So in this case, again, the pore space is black and the grains are this olive color. From that, we compute a signed Euclidean distance transform. So this is very similar to a normal Euclidean distance map, but we're measuring the distance in both phases rather than just one phase. So for every voxel that exists in the data, we're measuring the distance from that voxel to the nearest boundary, to the nearest two-phase boundary line. And then to keep the phases separate, we designate distances in the pore space to be negative and distances in the grain phase to be positive. And that distinction is a little bit arbitrary, but that's the convention that we've been using. So we just keep going with that. The other thing that I'll mention is that this is all in 3D. So the distance transforms and the filtration is calculated on the 3D data set, but that's very hard to visualize. So I'm only showing a 2D slice. Okay, so for example, the largest pore in this slice is this one that's sort of in the center right. And that has the largest negative distance value. And the largest grain that exists is this one here that's sort of center left, and that has the largest positive distance value. And once we have this distance map, we do a level set filtration through all the distance values. So at the minimum distance value, we just have this one Betti 0 feature. And then as we go up through the distance map, we start to get more and more Betti 0 features appearing. And the appearance of a Betti 0 feature is called its birth. And then as we continue to get closer to a distance value of 0, some of those Betti 0 features start to merge with one another. So the disconnected components are actually becoming connected, and we're losing Betti 0 features. So that's termed death. As this continues, we start to move into the positive distance values. So we're moving into the grain phase. And throughout this whole process, we're just keeping track of the distance values, where these Betti 0 features and where these Betti 1 features first appear, and also the distance values where they cease to maintain their topological structure. So in that way, we can keep track of the length scales over which these different topological structures persist. Okay, so we end up with 2 critical length values for every topological feature. Sure.
Excuse me. On the previous slide there, if you look at the largest grain, you're also, when you go sort of down to a higher resolution in the right, you also see that there's seems to emerge like a network with its own structural loops inside the largest grain. Is that a visual artifact, or yeah, exactly? So essentially the top of the mountain, the ridge of the mountain there.
No, that's not an artifact. So that's actually like the distance map that you calculate within that grain. Yeah. There is sort of a ridge along that, yeah, in the center region of that grain.
So does that have any significance, or is it just a pretty picture?
I mean, there are topological features that exist within the grain phase, and I honestly haven't thought too much about the grain phase because I usually focus on the non-wetting phase, but it's possible that that could tell you something about like the consolidation of the media, like how well connected those features are, or like the shape of those features at those as you're going through the positive values of the distance map.
Okay,
that's not a great answer to your question.
No, it was amusing and I wanted to ask it. Thank you.
Sure. Right, so we end up with 2 critical length values for every topological feature. So again, these are the birth and the death values of these features. So for a Betti 0 feature, the birth value is equivalent to the size of the ganglia body. When I say size, I mean like the radius of the equivalent maximal inscribed sphere of the ganglia body. And then the death value is the distance that's required for that body to connect to its to a larger ganglia neighbor. So I'm trying to illustrate that with these sort of cartoons that I've drawn here. For Betti 1 features, the birth value is the radius of the thinnest section that creates that loop. And then, so that's when that loop first gets formed, right? And then that loop dies when it fills in entirely. So it fills in entirely once the filtration has moved into the positive values that indicate the obstacle, the radius of the obstacle that the loop spans around. So hopefully that makes sense. Okay, so then coming back to this idea of persistence, the persistence is defined as the difference between the death and birth length scales. So here I've tried to draw some simple examples. So again, if you have 2 pore bodies which are right next to each other with a given birth and death value, if you have those same 2 pore bodies, but now they are connected by a much thinner throat, that would mean that the death value is further away from the birth value, so that's a more persistent pair of pore bodies. And then if those pore bodies are separated entirely by solid phase, that's again a more persistent set of features. In terms of Betti 1 features, if you have this loop around an obstacle, yeah, that's your first Betti 1 feature. If you have the same obstacle, so you're traveling around the same size obstacle, but your loop has a thicker radius, that will be a more persistent loop. And if you have a loop that's traveling around a much larger obstacle, even if it has the same, even if it's a very thin loop, if it travels around a larger obstacle, that is also a more persistent loop. So you can kind of think of this persistence as a measure of the spatial distribution of these features. Okay, so these birth and death measurements are compiled and illustrated in 2D histograms called persistence diagrams. So in these diagrams, the birth value is on the x-axis, death value is on the y-axis, and we can keep track of how these features are connected based on the sign, right? So negative indicates the pore phase or the non-wetting phase, and then positive indicates the solid phase, or basically just everything else that is the phase that not the phase of interest. Okay, so we can see over here on the right how the persistence diagrams for Betti zero features of non-wetting phase inside Bentheimer sandstone evolve as saturation level changes. So at low non-wetting phase saturation, there are lots of disconnected ganglia bodies and relatively few connected ganglia bodies. As you're moving to higher saturations, we're getting more and more connected ganglia bodies rather than disconnected ganglia bodies until we get to approximately 100% saturation, and then almost all of the non-wetting phase is connected. Next one. Okay, so similarly, we can look at the persistence diagrams for Betti 1 features. I'm not going to go through all the different possibilities of loops that can exist. I'll just point out that the loops that we're most interested in are these loops that are formed in the second quadrant. So these are like true loops that are formed by the pore space or by the non-wetting phase that are actually going around solid obstacles. And again, if we look at the persistence diagrams for these different saturation states, you can see there's hardly any loops at the low non-wetting phase saturation state, slightly more loops in the scan that was at 55%. And then obviously the most number of loops are at the 100% saturation state. Okay, and finally, when we're looking at Betti 2 features in these diagrams, so this maybe comes back to the question that was asked earlier about the solid phase. As we're going through this filtration process, eventually we get to this point where we're eroding away the outer edges of the solid phase. And at that point, we're starting to disconnect the grains from one another. And so that's when we're starting to create these Betti 2 features when we're thinking about this filtration process. So basically, we're isolating all the grains or the conglomerates that comprise the obstacles that are non-wetting phases flowing around. So again, what we see in the persistence diagrams here are that we have really large obstacles in these low saturation states. And I guess I should point out that the y-axes on these plots are not all the same. So the y-axis here is, I think, 140. This one is 120, and this one's 50. So actually, these two, the features that are in the top two persistence diagrams are much larger than the ones in this 100% saturation state. But sorry, basically the point is that the obstacles are large at low saturation levels, and then they're getting smaller and smaller as we get to 100%. When we get to 100%, now we're basically just measuring individual grains, right? Okay, so just to emphasize this a bit more, what we can get from these are traditional size distributions. So for example, we get the pore size distribution by looking at the Betti zero birth values. We get the throat size distribution by looking at the Betti zero death values. And we can also get a grain size distribution by looking at the Betti 2 death values. Okay, we can also get quantification of properties that are relative to connectivity. So this is an example from my colleague at ANU, Vanessa Robbins, and she's been a pioneer in this particular topological data analysis technique. And what she showed in this paper was that looking at a range of different classes of porous materials, if you look at the throat that corresponds to the most highly persistent Betti zero feature, so that's the depth value of the most highly persistent Betti zero feature, that throat represents the critical length for the porous media. So of course, the critical length is important for a range of different percolation related topics, but maybe one of the more well-known places it comes in is in the estimation of permeability from the Katz-Thompson relationship, which says that permeability is proportional to that critical length value squared. And she found that this correlation works really well for most of the materials she looked at, maybe with the exception of this really complex carbonate sample that was on the far right. Okay, so we can go back to the original problem that I talked about first, which is that we have this issue that these measured topological values, the Euler characteristic Betti numbers, are dependent on image resolution, but they can also be significantly impacted based on how much noise removal we decide to do. So how can we use the persistent homology analysis to address these issues of noise or small features and also image resolution? So one thing that we can do first is we can just figure out what these relationships are. So how do these parameters vary as a function of length scale? So that's what I'm showing here. Going back to that imbibition data set that I discussed earlier, you can see that for the Betti zero features, there's, for all cases, like large numbers of Betti zero features, very small Betti zero features. And then for the partially saturated data, at least, there's a bit of a plateau, maybe not so much for the dry scan. And then that same trend also holds for Betti one features. So knowing that, we can start to apply that knowledge with, especially when we're considering like a noise threshold or a, like if we want to remove small features from our digital images, what should that threshold value be to ensure that we're not biasing our topological measurements, right? So here I've calculated the non-wetting phase Euler characteristic, depending on whether, like, what size of noise removal I've applied. So basically, I say I'm only going to include these individual Betti zero features if they're larger than a certain size. And it's clear for all data sets that the Euler characteristic decreases when we exclude larger and larger Betti zero features, right? So we're getting rid of some of these small isolated components. So that makes sense. Then there's a point where the Euler characteristic is more or less stable over length scales. And then if you continue to remove features, you get to a point where you've removed all of the small features and only the largest connected cluster remains. So from an image analysis perspective, I would like to remove these really, really small features, which I'm not sure if they're noise or real features or what those are. But I would like to stay within a range where the Euler characteristic is somewhat stable, so that I'm not worried that my measured values are going to change significantly depending on like small variations in a noise removal threshold. So basically from these plots, you'd probably pick something in this central range as your noise removal threshold. And in fact, as I said before, when we did apply a noise removal threshold to these data sets, we picked a radius of 9 microns. So that was basically at the center of this plot. The persistent homology analysis can also help us decide what voxel size or what pixel size should be required in order to adequately visualize relevant features. So for example, if we want to make sure that we're resolving all of these redundant pathways in the Betti one features, we can look at the birth size distribution for the Betti one features. And here we can see, especially for the partially saturated samples, that they're fairly stable curves for thresholds that are less than about 6 micron. Of course, the dry scan still has significant numbers of smaller loops. So I guess the rule of thumb that we usually use is that we want our voxel size to be about 3 times smaller than whatever feature we want to visualize. So at least for the partially saturated data, if we want to make sure that we're visualizing all of the connections, which are at a size of a radius of 6 micron, that would be a diameter of 12 micron. So in that case, the maximum voxel size we want to use is 12 divided by 3 or 4 micron. So this is really useful information in terms of setting up your experiments. If you want to ensure that you're going to be able to image the relevant features, this tells you something about what voxel size you should aim for. But yeah, then again, you might need to be imaging at a higher resolution if you really want to be able to capture all of the loops that are present in the dry scan based on this. Okay, so we can use the persistent homology to help inform our data acquisition and our processing, but these length values also have physical relevance. So we can use these quantities to help describe and predict physical properties as well. One of the ways that I've tried to do that is by combining topology with length scale information by weighting topological features with their size or persistence values. So for example, for many flow processes, especially for non-wetting phase flow processes, the size of pathways in pore bodies is really important, and very small features can be less important. So weighting these topological features by their size or by their persistence, we can reduce the impact of these very small or very spatially close features. And an example of this approach is a structural measure that we defined that we called the persistent homology based aspect ratio. So in this case, we were looking at non-wetting phase trapping during drainage and imbibition cycles. So we did a series of drainage and imbibition experiments. We were looking at how the structure of the non-wetting phase would be related to subsequent capillary trapping. So we measured all of these features of the non-wetting phase after the drainage process. So we measured the size and the persistence of every Betti 1 feature and the size and persistence of every Betti 0 feature. Then we took the ratio of those values, and that's our persistent homology based aspect ratio. So in general terms, we're looking at the number, the size, and the persistence of all the redundant pathways of the non-wetting phase relative to the number, size, and persistence of all of the pore bodies that the non-wetting phase is occupying. So intuitively, if this value is very large, then the pathways should dominate and that should facilitate mobilization. And if it's small, that means that the ganglia bodies dominate and that should encourage trapping. And I'd point out the formulation of this structural metric is similar to other geometric values that people have used to predict trapping in porous materials. So for example, the ratio of the size of throats and bodies is something like an aspect ratio, and the ratio of the frequency of throats to pore bodies is something like a coordination number. So the novelty of this quantity is that it incorporates persistence and then it combines all of these things together in one number. Okay, and so the end result here was that for all of these experiments where we did these drainage and imbibition experiments and generated these trapping curves for different porous media, when we instead looked at the trapping efficiency as a function of this aspect ratio, this persistent homology based aspect ratio, all of the trapping curves collapsed to a single relationship. And so that indicates that for these samples with this formulation, we were able to adequately quantify the structure of the fluid phase such that we could look at the structure and then be able to predict how much of that fluid would be eventually trapped, but assuming a capillary dominated flow regime. Okay, so going back again to this issue of resolution and noise, we then calculated that ratio again for our new data set, and for data sets where we removed the noise or the small features, and also for the data sets where we hadn't removed those features. And we also looked at that ratio over the range of voxel sizes that I talked about earlier. And what we see here is that because we're incorporating these factors of feature size and persistence, the ratio that we calculate, that persistent homology-based aspect ratio, is it's relatively robust to the presence of small features and also to resolution impacts. So again, you can compare that to the classic Euler characteristic value, which shows pretty significant variation with noise resolution, or sorry, noise removal and resolution coarsening. Okay, so I think I have time to talk about one more example. And this has to do with pore networks, pore throat networks, and how we're actually extracting pore throats and pore bodies from digital images. So one standard approach, and one that I've used, is to use a watershed transform, which is, of course, based on the Euclidean distance transform of the pore space. And you can combine that with some geometric constraints to generate a pore partitioning. We can also get pore partitioning based on the persistence analysis, which is just subject to these topological constraints. So I've done the labeling for the same data sets. You can see the results are fairly similar from a qualitative perspective. So there are some subtle differences. Maybe like this pore body is more partitioned in the persistent homology labeling than in the watershed transform. And there's also some subtle differences in where the pore throats are identified. I did want to point out that in the watershed algorithm, in the partitioning algorithm I used, there were 10 user-defined inputs. And in the persistent homology algorithm, there's just one user-defined input. So the degrees of freedom are much higher when you're generating this pore partitioning using, or at least in the implementation that I use, in the watershed algorithm that I use. There is a lot more opportunity for the user to maybe bias the results a bit. And then I've just calculated some standard statistics based on the pore networks that I extracted from the pore partitioning. So in these plots, the black is the watershed-based partitioning and the red is the persistent homology-based partitioning. Basically, we see that there's similar aspect ratios. So we end up with similar geometrical properties for both networks. The persistent homology-based network produces slightly smaller throat sizes, and that's especially noticeable when you get to the large voxel sizes. And then same with the coordination number. So the persistent homology-based network maintains its connectivity better, even when you're at the coarsest resolution. So this indicates again that the persistent homology labeling approach is more robust to some of these length scale effects. Okay, so that I guess brings me to the end. I guess the things that I'm hoping that people take away from the talk are that these classical topological measurements are highly sensitive to noise and resolution. Betti 1 features are maybe more robust than Betti 0 and the Euler characteristic to noise, but all these topological features are impacted by resolution coarsening. And so this is something that really needs to be considered, especially when you're looking at topological measurements based on digital images. And one of the ways that we can start to address this is via topological data analysis techniques like persistent homology, because they allow us to link topology with length scale. And this can help us to inform data treatment in terms of noise removal or what resolution we should target. But it can also give us insight into physical properties like the size distribution and capillary trapping and pore network model generation. So I guess I just want to acknowledge my collaborators, including Ruotong, who's the student who acquired this new data set that I've mostly focused on, and Vanessa and Adrian, and also funding from the Australian Research Council. And most of the, these were the papers that I referenced most closely in the talk. So if you have, want to go read about it some more, then there's the citations there.
Thank you very much, Anna. There's now we start our question part.
Hello, this is Carl Fredrik here. Can you hear me?
Who's
Carl Fredrik, can you hear me?
Yes, we hear you.
Okay, good. I have a couple of questions, Anna. Nice talk. I wonder if you could go back to the slide where you were looking at the resolution and how that affected your different measurements. That was quite early on.
Maybe this one or back one more?
Yes, this one. especially for the last one there, you see that it really diverges, right, when you're going up in resolution. So in some sense, you don't have stable properties, right, when you have the ultimate resolution. So for this to work, I guess you need to have some sort of smoothing of your system, or you need to sort of disregard the finer structures. Do you agree?
So I think I agree, for particularly for the dry scan. I think that that's the case, but also I think that, so for this specific sandstone that we're looking at, what we were finding is that these the really fine topological features are mostly associated with the clay phases, like the microporosity and the clay phases. And so it sort of starts to depend on whether you think, particularly for this, I mean, Bentheimer sandstone is a pretty clean sandstone, and where you do have clay, it's like disconnected, right? You don't have a continuous clay phase. So it starts to depend on whether you think that that clay phase is really important for the transport properties that you're interested in or not.
Yes, and
yeah.
I guess for most transport properties, say fluid flow and permeability, those smaller features are not important, right? And also for a displacement process, they are not important. So in some sense, there already exists a length scale that you need to include here due to the transport or displacement process you're looking at. And when you later show this critical length scale from the work of Robin, was it? I don't remember. I in some sense feel like it's going the wrong way around. Wouldn't it be better to sort of know upfront what kind of length scales is actually important for the process you're looking at, and then using those persistent topology measurements at that sort of scale?
At that scale. Yeah, I mean, that is a good point. I think one of the main things that my student and I concluded was that actually for this system, the resolution that we had is maybe overkill. Like, we don't actually need to have close to 1 micron resolution for this sandstone. But we also decided, basically we figured that we don't want to have a voxel size larger than 6 micron. So that was one of the conclusions of her study, was that like there is a range that we would target, and there's a maximum and also kind of a minimum. I think the point that you make with the critical length scale, let me just go to that slide. Yeah, I think that is a good point. I think that's fair. I guess at this point for this particular paper, the main conclusion of it, like the main novelty of the paper, was actually just showing that this, like, they weren't actually interested in the fundamental property of the media, but rather just like what can you pull from the digital image, right? So it was just kind of making the connection between different digital image analysis techniques. But I think that is a good point that that you bring up, that there is some length scale that we are already interested in.
Because I guess if you're looking at the permeability, you will get estimate of what kind of length that could be, right? Since the other properties are not varying that much. Or if it is a displacement process, the actual pressure you're looking at through the curvature of films could then be another measure of where you, in some sense, want to do your cutoff in smoothing of the system before you're looking at the topology. Yes. Yeah, thanks.
Okay, thank you, Carl Frederick, for the question. Is there any more questions?
if there's nothing else, maybe I might ask this is Per Arne in Oslo again. So when you're looking at the Euler characteristic, you're essentially projecting the three-dimensional space of the Betti numbers onto a single number. Would there be any sense in looking at it as a path in the three-dimensional parameter space, and then it would presumably, as you get to a simply connected system, you would end up on the Betti 0 = 1 plane? And does that add any understanding about the structure? Thank
you. I think I need to think about that a bit more. I'm not quite sure off the top of my head.
Neither am I. It's just struck me. I've never thought of the Euler characteristic as a projection onto a scalar of a vector space of Betti numbers before. So it just came into my head as I was watching this.
Yeah, no, that's very interesting. I think I have to think about that.
Okay, if you have any thoughts about it, please let me know.
Yeah.
Okay, thank you. It was a very interesting talk. I really enjoyed it.
Oh, thank you.
Yes. And okay, Mario want to ask a question? Yes, please.
Yes, good morning, everyone. This is Marios Valavanidis from Athens, Greece. Very interesting presentation, Anna. I just need to understand, could you please go back to the previous diagram of the birth-death level sets, these kind of diagrams? Okay, and I would like to understand each diagram refers to a single snapshot of an ongoing displacement, or is it a series of snapshots, or is it a collection of data from a period of time incorporating a few tens or hundreds of snapshots? Given that these snapshots are taken at constant flow conditions, if this is possible, if this has any relevance to the actual experiments, the displacements.
Right. Yeah. So in this case, for these diagrams, so these were all quasi-static flow experiments. So some flow injection, some amount of fluid injection, and then an equilibration period so that we don't get interfaces moving in the scans, and then one scan. And then so each diagram is just based on the non-wetting phase distribution in that quasi-static state. So it's not under continuous flow conditions. The imaging, the microCT systems that we have, they're not built for speed of scans necessarily. So each scan, I think, is for this case it was about an hour, maybe 2 hours for each scan, but we tried to ensure that the fluid states were stable during the scan acquisition.
So you think that these diagrams would somehow, if you had the time or if you had the equipment to reduce this scanning procedure to a second or 2 or 3 seconds, would you think that these diagrams would be robust, meaning that they would create an envelope of data points, and these could be correlated to the flow properties or to the flow conditions? I mean, the shape of this envelope or the structure of this distribution of the points, of the data points, could this be correlated to the flow conditions somehow? Would it be too much to expect such a correlation?
I mean, I think so. This is sort of an open question, right?
Yeah.
Like whether these quasi-static experiments adequately or accurately reproduce what we would see in a continuous flow experiment. Whether this, sort of slow equilibration period, does that actually, are we somehow biasing the distribution of fluid, or is this actually what you would see, like knowing that we have ganglia disconnecting and reconnecting and these sort of like intermittent connectivity in a lot of cases during flow? Like, would this be equivalent to a snapshot of a dynamic flow process? I'm not exactly sure, but I do think there are data sets out there that I think there's dynamic data sets available that I could look at, and then we could just see if I could just match the saturation condition and the flow rate condition and to try to see if how much they do deviate. But I haven't done that yet. So
yeah, I understand that reducing the time to scan and create this and grab this information is a golden grail for the experimentalist. Yes, and that could open new pathways there.
Mm-hmm.
Okay, thanks a lot.
Yeah, thank you.
If there are no other questions, I can have another one maybe. And this is a bit more non-scientific and grumpy. Why do you call it persistent homology and not persistent topology? Because to me this is
I don't know.
not really homology.
I didn't invent the technique. I don't know.
No, okay. Yeah.
I think there is actually like a more mathematical. I mean, I'm not a mathematician, right? But I think there is a more precise mathematical definition of homology that is beyond my understanding. That is why they call it persistent homology and not persistent topology.
Yeah, because in my world, homology is to basically associate modules to a geometrical object, and I don't see the modules here. So I think it would have been more correct to call it persistent topology.
Yeah, I'll bring that up with the topologist.
Thanks.
Okay, great. Is any more questions? No? Okay, it's almost almost 1 hour now. Thank you very much. Is Mario has more questions? Yes.
Yes, last minute question. Sorry. I was wondering, Anna, would it be possible to have two scanners at the same time from different sensors? Working, two different sensors scanning your specimen on a very small shift of time. So there is a grabbing of information from one sensor, and they get these 2 hours time, and then you have another sensor grabbing on a small time shift.
So actually, yes, I think that. So this is something that we're looking at the CT lab. So I didn't really go into like the acquisition details, but the acquisition here, when they say space filling, what it means is that the scan is not contiguous. So instead you take one frame at this angle, and then there's a large shift in angle, and you take another frame. A lot of CT scans, they take contiguous scans. So it's like you take a frame, slightly rotate, take a scan, slightly rotate, take a scan, slightly rotate. The data that I showed you, the step spacing between each radiograph acquisition is very, very large. And what that means is that you could go back and rather than use like the entirety of all of the radiographs, you could just do a subset, if that makes sense. So it is possible to get a smaller time interval of the data. But I didn't do that in this case because what we really wanted was the high resolution data. But that is, I think it is possible to try to get smaller time windows of data, and then you can potentially get closer to dynamic imaging with our laboratory setups. Yeah.
Okay, thanks.
Yes. Okay, great. Then, Anna, if there's no more questions, then we will end up today's lecture. And thank you very much. It's a very nice presentation, and we are looking forward to hear more from you in the future.
Yay! Thank you very much for inviting me, and also thank you to everybody for showing up early to listen.
Yeah. Okay. Thank you.